Okay, so this video, guys, is looking at the chemical reactivity of group 1 metals, and specifically the group 1 metals, and we're going to analyze their reactions with water. Now, what we need to be able to do here today is, first of all, have a look at these reactions. Look at the observations. So what do we actually see that's going on in each of these reactions? Second thing then is we need to be able to explain these observations. So, whatever we see, how can we explain that from a chemical standpoint? Next thing we need to be able to do then is to write the balanced chemical equations, or the BSE, the balance symbol equations, for the reactions that we see going on the screen. And we also need then to state and explain. So we'll just say describe the trend in the reactivity of these group 1 metals with water. So in other words, if we think about the group 1 metals from the periodic table, we would have lithium at the top of the group, followed by sodium, followed by potassium, and then there's two that aren't in the syllabus, which are rubidium and cesium, these two down here, but we're going to have a look at them just to confirm the trend. But we need to be able to state and explain what we see with water with each of these three, and then we need to have an idea of why the reactivity changes as we go down. So do they become more reactive? Do they become less reactive? And we also need to be able to state and explain, well, what is it that's actually produced in the water when these reactions occur. So we'll have a look at the reaction of lithium first and foremost with water, and then we'll work our way down through these metals and see how they change. So this is some lithium you can see in the screen at the minute, and what we have here, there's not a huge amount to see in terms of what goes on in the flask or the beaker here. I would say there's some universal indicator in this water, hence the reason why it's green, and we have a pH sitting at about 7.3, so it's just normal water. So what we'll do is we'll hit play here, and what I want you to do is try and pick out really the couple of key observations, and if you can do this for each of the reactions that I show you on the video, and then what I will do is I'll cover the key observations after that, and you can just check if you got the same observations that I get, and really the ones I get are the ones the examiner will want you to state. So that rather annoying noise in the background there is just a little stir in the you can see it there at the end of my cursor, just a little stir in the beaker, a magnetic stir. So you should have one observation already there. You should have now your second observation, fairly significant. Okay, so if we get rid of that, the two observations that I would pick out there, and they're not all the observations because there's a very small amount of lithium used because it's a very highly reactive metal, were first of all the change in pH. Okay, the pH went up till about, if we just go back to it there, it's up till about 10.5, so it started off as a neutral pH and it's taken itself up to about 10.7 there. If we'd also look at the universal indicator, I'll just write UI there, and it went from green. We always write the initial colour of something in chemistry, it's just good practice to do so. It went from green to purple, okay, via blue. Now what does purple mean? Well, purple, hopefully you can remember this from key stage 3, tells me that we've now got a strong alkali. So I suppose the question is, can we sort of start to work out what's being made in here? Now there was no solid product, so the reason why I've said alkali here is because something that turns the pH above 7 if it's soluble, is referred to as an alkali. So if we look at our chemical equation, we have lithium. I'm not going to write word equations here, you should be able to work those out yourself. Lithium plus water gives us a soluble metal alkali, and you should know from previous studies that that is lithium hydroxide. Now there is something else produced in this reaction, but we can't quite work it out as yet. You might say to me, well, how do you know that that product is soluble? Well, because it formed a solution. There was no solid formed in that beaker at any stage, so it's fairly obvious that it was indeed a solution. So hopefully you were able to pause that video and get the same observations that I got after it. So what I'll do now is I'll go to the video of sodium with water, and we'll have a look at how it reacts. And again, if you just watch the video, and then I will go over the key observations from it, and then we'll go over, try and construct the equation, and with the sodium we should be able to fill in the gap that I've just put the question mark on there. Okay, so we'll get this video of sodium up and see how we go. Okay, so this is the sodium, and again we have some universal indicator in here in the water just to show that it begins neutral. So we'll drop this in, just have a listen and a look and see if you can get the observations. Okay, so you can rewind that and have another look at it, but I'll talk you through the main observations here now. So the first thing is, if we just will go back, we can see that hopefully the sodium floated. So that tells us that the sodium is less dense than water. That was clear and obvious if we just listen to it here as well. There's definite fizzing. Now fizzing in a chemical reaction tells me that there must be a gas getting produced. Now we can't identify the gas just yet, but we will be able to soon. Now if you heard that, hopefully it came up in the video with a squeaky pop. Okay, now that should tell you which gas is produced in this reaction. That will allow us to fill in our missing gap in the previous equation. So the gas is indeed, of course, hydrogen. Okay, now let's have a look at the colour change in the universal indicator. You can see it's turning fairly clearly blue purple colour, so there's again a strong alkali produced. And what you'll also see is we're getting an explosion there, which means there's lots and lots of heat given off, and eventually we get a solution produced, which means again that our product at the end here is of course soluble. So let's go back to our equation, and we'll construct the equation again this time, but for sodium. So sodium, of course, and again reacts with water, and again we get this alkali and it's soluble. Okay, pH well above 7, which is of course sodium hydroxide, and this time we can identify the gas as being of course hydrogen. Now if you look at the equation, so the previous equation, we can just finish it off now, in that we have of course lithium reacting with water to give us lithium hydroxide and hydrogen. So you can see a trend here in that, as we would expect, everything in group 1 has similar chemical reactivity, hence the reason why they're all in the same group. So when they're in water, the commonality is that they all produce the alkali, the metal, hydroxide in this instance, and hydrogen. These things are called alkali metals, so it's no surprise that when they're in water they do produce this. So let's have a look. There's a problem with our equation, of course, in that on this, on the right hand side here, we have a hydrogen here and we have 2 hydrogens here. So in total we have 3 hydrogens, whereas on the left hand side we only have 2 hydrogens. So we're going to have to balance out our hydrogens here. So therefore, how do we do that? Well, we've 2 here. I'm going to put a 2 there, because we've got to have multiples of 2. So that gives me 2 times the 2. So that gives me 2 hydrogens in that compound, and of course 2 hydrogens in this compound. In order to correct that, on the left hand side, I need to put a 2 there. So that gives me 2 multiplied by 2 Gives me 2 hydrogens there. Gives me 2 multiplied by 1. Gives me 2 oxygens. Let's just check out the oxygens on the right. Gives me also 2 oxygens. Now I've still got an imbalance in the fact that I have sodium just as I circle it there. So I have 2 sodiums on the right hand side of the arrow. So if I pop a 2 there, I also have 2 sodiums. So that's my equation balanced for everything. Sorry, I should say that went up from 2 to 4 because I have 2 hydrogens here and I have 2 hydrogens here. Now the next reaction we'll move on to will be with potassium. So again, I load up the video of the potassium with water, have a look at it. This time I want you to have a look and see if you can get the observations, of course, but also if you can start now to coming up with how the chemical reactivity changes as we move from sodium down the group to potassium. Okay, so if we have a look at the reaction of some potassium being popped into water here. So just let it run here, you can work out your observations. So first thing you should have noticed was, of course, it floated. The second thing you should have noticed was that it ignited with that sort of lilac-y purple coloured flame. Really, as soon as it hit the water, unlike the sodium, which required someone with a lit splint to come in and light it. So it's really very, very exothermic. Loads of heat given off. The hydrogen gas actually just ignites itself because it's so hot. Hard to see the indicator turning purple there, but it does. Certainly floats. Certainly the metal again disappears and dissolves. So the product again must be soluble. So we should start to be able to see a trend, because certainly that reaction that we just looked at was considerably more exothermic than the reaction of the sodium or indeed the lithium. So again, we'll just have a quick look at it, but hopefully we're starting to pick up the trend now. So of course this one is potassium reacting with water. Hard to see it there, but the product did turn the universal indicator purple, so it is indeed potassium hydroxide. There was fizzing and the gas ignited itself. This time there was so much heat produced, and again the equation balances itself in exactly the same way as the previous. So again, our observations are the same as the last two, although it wasn't particularly obvious for the lithium reaction, but it was obvious for the sodium, in that the metal floats. The metal, if you looked at in both instances, disappears. The universal indicator, just write UI, turns, and again green, as I've always said, always give the initial colour and the final colour. So it goes from green to purple. Of course you get a fizzing. Okay, huge amount of heat produced in this instance, even more so in the previous reaction. The whole reaction could certainly be described as being very vigorous. Okay, it's highly reactive. This is why you store sodium. If it's found in the lab, it's stored in a jar or a bottle under oil to prevent any water or oxygen getting to it. And that's really about the height of it. Again, we can correlate the potassium hydroxide to the purple. Okay, potassium hydroxide, metal hydroxides are of course alkalis. We can correlate the fizzing to the formation of hydrogen gas. The heat, we can just say, is proof that the reaction is exothermic. Floating, we can talk about density, and that the potassium is less dense than water, and the fact that it disappears means that our product, which is this substance here, is hopefully you're able to work out is of course therefore soluble. Okay, so in our next video we're going to have a look at rubidium and cesium. Now these two are not on the syllabus, but it's quite interesting just to have a look at them so that we can see the trend in group 1 metals as we descend the group. We started off with lithium, worked our way down to sodium, just did potassium, rubidium is below potassium, and then we'll get down and have a look at cesium as well. So we look at these two, they're not in the syllabus. The observations are very similar to these, the products are similar also. So that's rubidium. You can see highly explosive, and that demonstrates the trend that the group 1 metals become more reactive again as we go down the group. So we'll show you that one more time, and the fact that it explodes with impact on water. So it doesn't really have time to float or dissolve or change the universal indicator colour or anything like that. Okay, so quite clearly even more reactive. We'll have a look then at the last one here, which is the cesium, and you can see immediately the person who's been brave enough to put this into the water has worn very thick gloves and used tongs. So we'll have a look at that and see how reactive so highly reactive, you can see even more reactive than previously. One thing I want you to have a look at is what happens to the cesium as soon as it's put into the water, and you can maybe see it on my cursor there now, and that it sinks, so it doesn't float anymore unlike the other group 1 metals, and that's a sign that as you go down the group, density increases. So you can see loads of fizzing. It's just about, see it maybe on the screen, that it fizzes rapidly and it's really exploding. You can see the bubbles there quite clearly, and it's those bubbles being made in such a small volume in such an enclosed space that causes the bowl to explode. The amount of gas being produced really quickly at high temperatures causes the gases to expand, and the bowl then just blows up. So we'll play that one more time. Okay, so you can see it blows up from the bottom down because the metal has sunk this time. Okay, so we'll just shut that down. Right, so in summary then guys, we can see that the reactivity of the group 1 metals as we descend the group increases. We can see that also we just discovered that all of the group 1 metals, when they're reacted with water, will give a metal hydroxide and hydrogen. And the good thing here means that you only really have to learn one reaction. So you just have to learn that the metal, if we represent it as M, two of them react with 2 moles of water to give us 2 moles of the metal hydroxide plus hydrogen. You only have to learn the observations on one occasion, and that they float, the metal disappears, the universal indicator turns green from purple, but don't write that unless the examiner says there actually is universal indicator in this solution. It fizzes, loads of heat's given out, it's a very vigorous reaction. Those are all your observations for all of them, but what you must remember is that as you go from lithium to sodium to potassium, they get more and more vigorous. Okay, so our next video will be on the explanation as to why these reactions get more vigorous as we go down the group. So I hope you find this useful.